Okay, let's dive right into this explainer. Today, we're looking at a literal clash of titans. The centuries-old, totally unbreakable laws of classical physics going head-to-head with the weird, rule-breaking world of the quantum realm. We're looking at a truly fascinating piece of research about an optimal superconducting hybrid machine. And honestly, it fundamentally challenges everything we thought was possible when it comes to the strict trade-offs between energy waste and precision. For engineers and physicists, what we're about to explore is nothing short of a scientific heist.
So here's our roadmap for today. We'll start with the ultimate trade-off, meet our hybrid machine, explore the quantum loophole, and finally, look at the math behind breaking the rules.
All right, part one. The ultimate trade-off, the strict laws of classical physics. For centuries, the absolute holy grail of engineering has been a machine that works perfectly without losing anything to heat, friction, or waste. I mean, imagine an engine that produces maximum output without shedding a single ounce of useless energy. It's a beautiful dream, right? But classical physics, specifically the laws of thermodynamics, ruthlessly steps in and tells us, nope, that is impossible. Whenever you have a thermal engine generating power under a non-equilibrium situation, it is strictly guaranteed to generate a finite amount of entropy. You simply can't get something for nothing.
So, the crucial point here revolves around a principle called the Thermodynamic Uncertainty Relation. Let's just call it the TUR. Think of this as a strict classical law establishing an unavoidable trade-off. In the classical world, the certainty and reliability of your machine's output is heavily bounded by how much waste it produces. If you want a machine with incredibly high precision, meaning it delivers constant, reliable power without stuttering or fluctuating, well, you're forced to pay a steep, unavoidable tax in the form of massive entropy, or energy waste.
Think of it like a high-performance sports car engine. If you want massive, responsive power and absolute precision on the track, that engine is going to burn a ton of gas and generate a massive amount of blistering heat. You just can't escape it. In classical devices, you simply cannot have a perfectly smooth, constant output without shedding a massive amount of wasted heat in the process. The precision inherently requires the waste.
Moving on to part two, the hybrid machine. A microscopic marvel. Take a look at this incredibly complex setup designed specifically to test and break these very limits. What we have here is a device so profoundly small it operates entirely in the quantum realm. It features two nanoscale conductors known as quantum dots that are capacitively coupled. The bottom dot is connected to two normal leads, a hot one and a cold one. Meanwhile, the top dot is connected to a reference metal lead and, critically, a reservoir that generates entangled Cooper pairs. Now, Cooper pairs are essentially pairs of electrons that bind together and behave as a single entity, which is the exact mechanism that allows superconductivity to happen.
To put that in simpler terms, this means our microscopic device is a multi-terminal hybrid machine. Instead of a standard thermal engine that just has a single working substance sitting neatly between a hot and a cold bath, this device is plugged into multiple energy sources at the exact same time. This unique configuration allows it to multitask in ways that a standard, single-purpose engine simply cannot.
And what makes this setup truly incredible are its dual operating modes. It isn't just acting as a standard engine. It can operate as an engine and a refrigerator at the exact same time. Depending on how it's electrically or thermally biased, it shifts into different modes. We have RP, where it cools a reservoir while simultaneously pumping heat. EP, where it acts as an engine generating work while pumping heat, and ER, generating work while refrigerating. It's doing multiple highly complex tasks concurrently. Pretty wild, right?
Which brings us to part three, the quantum loophole, how to pull off a thermodynamic heist.
So how exactly does this tiny device manage to be so precise without paying that steep classical entropy tax we talked about earlier? Well, in classical physics, every machine has a strict thermodynamic balance sheet. This principle is called local detailed balance. It basically demands that all the forward and backward physical processes in the machine mathematically match up perfectly with the entropy produced. The classical probability is incredibly strict here. If this balance sheet holds, the thermodynamic uncertainty relation simply cannot be violated. No exceptions.
But our hybrid machine introduces a massive twist. Remember that top quantum dot? It's coupled to a superconductor, which injects those entangled Cooper pairs we mentioned. This triggers what are known as undreave coherent processes. In more accessible terms, this is a quantum phenomenon where particles are reflected in very strange ways that do not neatly reverse themselves. This injection of quantum coherence completely shatters that strict classical balance sheet.
By breaking the local detailed balance, The quantum machine actually pulls off the heist. It completely escapes the classical trade-off, because quantum states are non-local, meaning they don't just exist in one distinct, simple place like an apple or a baseball would. The old rules literally do not apply here. The machine harvests resources and generates useful currents far beyond classical upper bounds. It achieves incredible precision without the massive energy waste.
All right, part 4. Breaking the rules. The proof is in the math.
So we have the theory, but to truly appreciate this, we need to see exactly where the violation occurs. To do this, researchers use the multidimensional Thermodynamic Uncertainty Relation, or MTUR, which basically scales that classical limit up to account for a complex, multi-terminal machine. Take a look at this. If we map the machine's hybrid modes on the left and compare them to the energy fluctuations on the right, notice those dark blue and purple streaks? That exact boundary, right where the operating modes are switching, is the precise moment the thermodynamic limit completely drops below the classical baseline.
Right at these rule-breaking boundaries, the hybrid thermal machine can achieve a staggering efficiency of around 85%. Let's just pause and think about that for a second. We have a microscopic machine that's not only juggling multiple complex tasks simultaneously, but it's doing so at near optimal efficiency, blowing right past the absolute upper limit set by classical thermodynamics. It's just incredible.
So, what you should really take away from this explainer is that by deliberately utilizing quantum effects like coherence and entanglement, we can design the ultimate efficient machines. They multitask flawlessly with minimal waste, low dissipation, and incredibly small fluctuations. And the real-world applications of this, they are mind-bending. This research provides a tangible blueprint for future technologies. Imagine quantum processors and nanoscale computers that can run at incredibly high speeds and precision without ever overheating.
It leaves us wondering exactly what other limits of technology are just waiting for a quantum loophole to be discovered. If we can use entangled Cooper pairs to bypass a fundamental trade-off of the classical world that has stood for centuries, the future of nanoscale engineering is going to be incredibly exciting. Thank you so much for exploring this with me, and keep questioning the rules.